Hey guys, we're talking from page 664 today in our geometry textbook. 10.3, we're going to be applying properties of chords. Okay, so some vocabulary that we want to make sure that we're comfortable with is what exactly is a chord? And remember, a chord is just going to be a segment that connects from one point on a circle to another point on a circle, right? So I'm going to draw a quick little, example of that, right? If it starts here and ends here, hey, that's a chord, right? If it starts here and ends over here, looks like a diameter, guess what? Also a chord, right? Other things that we need to be comfortable with, or the definition of, is called an arc. Right? So if you look over at this circle, again, the circle on our right, we can see we've got a major arc and we've got a minor arc, and that is just the distance from one point following the edge of a circle to another, right? And we can measure that distance either by looking at the angle that can be created. That's a central angle or an inscribed angle. Sorry for the sloppy lines here. Or we could talk about just the length of that arc if we were to, measure that with a curved ruler. All right, so if the chord passes through the center of the circle, like the circle over here on the left, right? We see a diameter here. That diameter is in fact a chord, and that chord cuts this circle into two semicircles, right? I see this purple one here, it's a semicircle, and I see this orange one here, that is also a semicircle, right? If a chord is not passing through the center of a circle, then we've got just a regular chord, and it creates a minor arc. The minor arc is always the smaller one, and a major arc, right? The major arc goes around. That's that purple line. All right, so we're going to use that information to kind of move on into some theorems here. Okay, so I've got Theorem 10.3 written out for us, and it reads, hey, if we've got a circle, right, and we could name this circle, P. Okay, I've got circle P. So in the same circle, P, or we could have two congruent circles, and congruent circles are just circles that have a common radius or a congruent radius. All right, so in the same circle or in congruent circles, two minor arcs. So the minor arcs that we are talking about here, I'll use red. The minor arcs that we're talking about here are AB, arc AB, and arc CD, right? Those two minor arcs are congruent if and only if their corresponding chords are also congruent. So looking at this circle over here, we know that arc AB is congruent to arc CD if and only if segment AB, that chord, is congruent to segment CD, right? So that is Theorem 10.3. And there's a proof on page 670 of our textbook if you want to follow along with that. We are not going to have to do that proof. All you need to know is, hey, if I've got two arcs, how can I show that they are congruent? Well, show they're congruent by finding the lengths of those chords. Move on to Theorem 10.4. And this one, you can see I've got an example over here on the right. We've got a circle. Let's name this circle M. Right, I've got circle M, and I've got a diameter. It looks like, and I've got another chord, and it looks like they are intersecting. And it just looks about like that one chord, the longer one, is a perpendicular bisector, right? And we can see that here. I'll go over the orange with the red. It's a perpendicular bisector of our second chord, right? It's perpendicular, creates 90-degree angles, and bisects segment TU. If you have a chord that is a perpendicular bisector, then that chord has to be the diameter, right? SR, chord SR is a diameter. That's what we can conclude if we know it is a perpendicular bisector. And vice versa, Theorem 10.5, well, if the diameter of a circle is perpendicular to a chord, right? I see EG here. The diameter of this circle is perpendicular to chord DF. That means that EG must be a bisector to DF. So I know that it has to bisect this chord, and it bisects this arc, right? So we usually don't write, I'm going to erase those because we usually don't write those tick marks to show that DG is going to be congruent to GF, right? What I would say is, hey, what I know, since EG is a bisector, is a diameter that bisects, and is perpendicular to DF, then I can state that DG, arc DG, is congruent to arc GF. Right, so we know EG is a diameter, we know it's perpendicular, so therefore it bisects DF, right? DH, segment DH, is going to be congruent to segment HF, and it also bisects the intercepted arc DF, right? So DG is in fact congruent to GF. Theorem 10.6. Back to talking about the same circle or congruent circles, right? So in the same circle or congruent circles, two chords are congruent if and only if they are equidistant from the center, right? So I've got two chords here. I've got AD and I've got BC. I've got AD and BC. And I can state that AD, segment AD, that chord, is congruent to chord or segment BC if and only if those two chords are equidistant, right? Only if they are equidistant. So that means I'm talking about these guys right here. Right? I'm talking about these two segments. We notice that FE, this line right here, oops, I need to make sure that I am dealing with the correct pen. It's perpendicular, right? Because I'm talking about the distance. I'm talking about the distance from the center to that chord. I'm talking about the distance from the center to this chord over here. If those are perpendicular and congruent, right, the distance FE is equal to the distance EG, then I know that chord AD is congruent to chord BC. This is a theorem that you guys are going to be using quite a bit on your homework. All of these theorems really you're going to be using quite a bit on your homework and your tests. Notice your tests are going to be a little shorter than what you're used to, which I think is great. But you guys let me know if you have any questions. I'll be available.